In this lecture, we will discuss about some properties regarding the Bessel's equation. Now, we have already known the structure of the Bessel equation or the form of the Bessel equation. Now, in this lecture, we will show that some equations can be reduced to the Bessel's equation. So, let us look at equation number 1. Equation number 1 is x square d square y by dx square plus x into dy by dx plus k square minus x square minus n square into y is equal to 0. Now, this equation can be reduced to the original form of the Bessel's equation if we, that is, rearrange this equation by some special type of substitution. For example, in this equation, if we put t is equal to kx, then dt by dx will be k, dy by dx that can be written in this way, that is dy by dt into dt by dx. Now, dt by dx is equal to k, so that can be written as k into dy by dt. And d square y by dx square, that can be written as ddx of k dy by dt, because dy by dx is equal to k into dy by dt, which was proved in this step. So, ddx of k into dy by dt, and ddx that can be written as ddt into dt by dx. Here we have written dt by dx to balance this, and inside that is k into dy by dt. So, that can be written as k square into d square y by dt square. Now, what we have to do? We have to substitute the values of y, dy by dx and d square y by dx square that we have deduced in these steps in equation number 1. And after this substitution, that equation number 1 will be like this. And if we simplify this equation, that is, if we suppose multiply by k square, then this equation will be like this: t square into d square y by dt square plus t into dy by dt plus t square minus n square into y is equal to 0. Now, if we look carefully to this equation, so this equation is like the original form of the Bessel's equation, and we know that the solution of the Bessel's equation is y is equal to c1 jn of t plus c2 j of minus n into t. So, this will be the solution of this Bessel's equation. Now, as we have assumed t is equal to kx, so the solution of this equation will be y is equal to c1 jn of kx plus c2 j of minus n into kx. So, this is the solution of equation number 1. Similarly, suppose we have another kind of equation, that is equation number 2 here, that is x into d square y by dx square plus a into dy by dx plus k square into xy is equal to 0. That is equation number 2. This equation can also be reduced to the original form of Bessel's equation after some substitution, and we have to know the tricks of the substitution in each case. For example, in the previous case we assumed t is equal to kx, and the form of the equation dy by dx was replaced in terms of dy by dt. So, in this case the tricks is that we have to assume y is equal to x to the power n into z. Then we have to calculate dy by dx. So, this is the value of the dy by dx. This is x to the power n into dz by dx plus n into x to the power n minus into z. This is the value of dy by dx. Next, we have to calculate d square y by dx square. So, we will get two terms from the first term. These are the two terms, and from this term we will again obtain two different terms. So, after some simplification, the d square y by dx square will be like this: x to the power n d square y by dx square plus 2n x to the power n minus 1 dz by dx plus n into n minus 1 x to the power n minus 1 into z. So, this is the equation for d square y by dx square. this will be z. There is a printing mistake, so y will be z here. Now after substitution, that is after substitution of dy by dx and d square y by dx square to equation number 2, we will obtain this equation, that is like this equation. Now we have to multiply x with the term in the third bracket, and we have to multiply a with the term in the second with the third bracket, and we have to rearrange them. So after rearranging and some simplifying, we are obtaining equation number 3. Now suppose if we divide equation number 3 by x to the power n minus 1, then we will obtain this equation, x to the x square d square z by dx square, like this. This is upon division by x to the power n minus 1. Now our aim is to reduce this equation to the standard form of the Bessel's equation. So we have to keep in mind that fact, and we have to continue our simplification process with that fact, that is somehow we have to convert these equations to the standard form of the Bessel's equation. Now you see that x square into d square z by dx square, that form is okay because this term is also in the original form of the Bessel's equation. But here apart from x into dz by dx, 2n plus 1 is multiplied. So we have to put 2n plus a is equal to 1. Then the second term will be according to the form of the Bessel's equation. So we will assume 2n plus a is equal to 1. Next, what we have to do, if we assume 2n plus a is equal to 1, then the term in the third bracket will also be simplified, and it will be converted. If we assume 2n plus a is equal to 1, and if we replace n and a in this from this equation, so what we will obtain, that k square minus x square minus n square, that is the terms in the third bracket, that will be reduced to this form, that is k square x square minus n square. Here you have to replace a with n. You see there is no a here, that means you have to replace a by n. Then you will obtain this form. Now you see that this form of the equation is exactly similar to the equation number 1. That means this form, and already we have obtained the solution of equation 1, that is c1 gn kx plus c2 g of minus n kx. So starting from this equation, what we have done, we have reduced the equation to the form of equation 1. That means we can calculate the solution of this equation. So solution of this equation will be c1 jn kx plus c2 j minus n kx. Now as the left hand side is z, and we have assumed that is y is equal to x to the power n into z, so we can write in place of z, we are writing in this way, that is y is equal to x to the power n, because z is equal to y by x to the power n. So y is equal to x to the power n into c1 jn kx plus c2 j of minus n kx. This is the solution of the equation number 2, where n is equal to 1 minus a by 2, because we have assumed 2n plus a is equal to 1. Now let us consider another equation, that is this form. Suppose x into d square y by dx square plus c into dy by dx plus k square x to the power r into y is equal to 0. This is another form of the equation. So what is the difference? You see that in the previous equation there was only x, but here x to the power r is there. Other things are almost same. Now how to reduce this equation? We are going to reduce in this way, that is we are assuming that is x equal to t to the power m. So t is equal to x to the power 1 by m. You have to proceed in this way. If x is equal to t to the power m, then dy by dx, that will be dy by dt into dt by dx. So dy by dt, now dt by dx, how to calculate? T is equal to x to the power 1 by m. So from that equation we are going to calculate dt by dx. So this is the expression for the dt by dx. and this is after some simplification. So this is the form of dy by dx. Now we will calculate d square y by dx square. So that will be d dx of dy by dx. So this is the value of dy by dx. Now d dx of this is dt of this into dt by dx, because you see here there is dt, those will be cancelled out. So ultimately we can find d square y by dx square by this expression. Now again we have to differentiate with t. So after differentiating with t, we will obtain this term, and for dt by dx we will write this term, because t is equal to this, so dt by dx will be this. Now you have to simplify this expression. So after some simplification, so we are obtaining this expression for d square y by dx square. Now you have to substitute dy by dx, d square y by dx square to the main equation. So after substitution to the main equation, that is equation number 4, we are obtaining this form of the equation. So you see that in the last term there is k square, and x to the power r has been replaced to t to the power mr into y is equal to 0. Other things are same. Now after some simplification we are obtaining this equation, and for further simplification what we have to do, we have to multiply this equation by m square by t to the power 1 minus m. So if we multiply this equation by m square by t to the power 1 minus m, then we will obtain t into d square y by dt square into 1 minus m plus m into dy by dt plus kml whole square into t to the power mr plus m minus 1 into y is equal to 0. Now what you have to do, that is there is a term multiplied with dy by dt, that is 1 minus m plus cm. Now what you have to do, that is you have to assume that that constant is equal to a is equal to 1 minus m plus cm. Actually what we are doing, if you carefully look at the equation, that is this equation, you see that in this equation x is multiplied with d square y by dx square, and a is multiplied with dy by dx, and the last term is k square xy is equal to 0. So our aim is to reduce this equation to the form of equation 2. So that is our target. So that is why what we are doing, that you see that the first term is t into d square y by dt square, that is similar to the previous expression. So this term, constant term in the first bracket, we are assuming as a. So now the first and second term becomes t into d square y by dt square plus a into dy by dt, that is exactly similar to this form, x into d square y by dx square plus a into dy by dx. Now we have to reduce third term in this way, that is so that it becomes like k square xy. So how to do that? You see that the third term is like this, kml whole square t to the power mr plus m minus 1 into y is equal to 0. Now we have to keep y as it is, just like this one, that is y, this one, that is y, k square x into y. So we are keeping y as it is. Now you see that x is multiplied with y, x means that is independent variable. Now as the present differentiation is with respect to t, you see that with respect to when we have replaced this equation, so this independent variable is t, so we have to keep t here. In this book there is some printing mistake, but you have to keep in mind, that is if you want to compare this equation to the previous equation, then you have to keep t here in this place. So how to keep that? You see that after multiplying by m square by t to the power 1 minus m, we have obtained, that is kmr whole square. That is this term is constant, so there is no problem here, because we are writing km in place of k. In the previous equation there was no m, but it was k square only. So in this equation km, we have to write km in place of k. So in km square we have no problem. There is y also there, just we have to keep t to the power 1. So how to keep t to the power 1? Then we have to assume mr plus m minus 1, that is equal to 1. So we will write mr plus m minus 1, that is equal to 1. We have to assume that. Then there will be t here, and that equation will be exactly similar to the equation 2. Now solution of the equation 2 is like this, that is y is equal to x to the power n c1 j n kx plus c2 j minus n kx. Now for x we have to write t, because independent variable is t. So this will become t to the power n, and for k we have to write km, and for x we have to write t. So if we substitute like this, then we will get the solution in this way, that is t to the power n, and for x we are writing t, c1 j n kmt, we are writing km in place of km, and independent variable is t. So c1 j n kmt plus c2 j minus n kmt. So that is the solution. Now in the last step you have to replace t again in terms of x, and you know the relation. This is the relation, x is equal to t to the power m, or t is equal to x to the power 1 by m. So if you replace t and write in terms of x, then this is the solution. So now we have learned, that is how to reduce some equations to the standard form of the Bessel's equation, and then we can solve that equation. Another thing we will learn in this lecture, that is orthogonality of Bessel function. So what is orthogonality of Bessel function? 0 to 1 x into jn alpha x into jn beta x dx is equal to 0, where alpha and beta are the roots of jn x is equal to 0. That means jn alpha is equal to 0 or jn beta is equal to 0. We have to show that. Now how we can show that? From the previous discussion we have already learned that some equations can be reduced to the standard form of the Bessel's equation. So we can write, that is x square d square y by dx square plus x into dy by dx plus alpha square x square minus n square into y is equal to 0, and here just in place of alpha we are writing beta. So equation 1 and equation 2 they are actually some variants of the Bessel's equation. So solution 1 and 2 are, we can write that jn alpha x and jn beta x, they are solution of equation 1 and 2. Now if we multiply first equation with z by x and second equation by minus 1 by x, and then if we add, then we will get this type of equation. Now you see the first term, that first term can be written in this way, that is ddx of x z dy by dx minus y dz by dx. If you differentiate this expression, then you will obtain this expression. So we can write the first term by this expression. Actually first two terms can be written in this way, that is ddx of x into z dy by dx minus y into dz by dx. This is for the first two terms, and last term is alpha square minus beta square into xyz is equal to 0. Now we will integrate this equation with respect to x and within limits 0 to 1. So we are integrating with respect to x. So if we integrate, so ddx of x into this, and here there will be another dx, because we are integrating. So dx will be cancelled out. So this is actually d of something. Suppose integration of dz is equal to z, and for this alpha square minus beta square is constant. So what we are doing actually, and this term we are transferring in suppose left hand side of the equation, and this equation to the right hand side of the equation. So we are obtaining this equation, that is beta square minus alpha square integration 0 to 1 xyz into dx, because you are integrating this with respect to dx. We have written that beta square minus alpha square, as it is a constant, so we have kept this term outside of the integration. And as this integration is like this, ddx of, suppose this is z, So dz by dx into dx. So dx will cancel out. So integration of dz is z only. So this is the result, and limit is 0 to 1. So only for 1 we will obtain the value, because limit is for x only. So in place of x we are writing 1, and z dy by dx minus y dz by dx is the result for x is equal to 1, and for x is equal to 0, that will be 0. That is why you have written x is equal to 1. Now putting the values of y is equal to jn alpha x, because y is equal to jn alpha x and z is equal to jn beta x. So if you write y is equal to jn alpha x, then dy by dx will be alpha into jn prime alpha x. Z is equal to jn beta x, so dz by dx will be beta into jn prime beta x. Now if we substitute these values in equation number 4, then we are obtaining equation number 5 after this substitution. So this is the equation number 5. Now we have to keep in mind that the right hand side is for x is equal to 1. So we have written x equal to 1 for all the values here, that is we have written 1 in place of x. Now we have to keep in mind, that is in the question it was mentioned, that is alpha and beta are the roots of j n x is equal to 0. That means j n alpha and j n beta is equal to 0. So wherever we will find j n alpha and j n beta, we have to put 0 over there. So with these values, that is jn alpha and jn beta is equal to 0, then the right hand side will become 0, because there is jn beta, jn alpha. So right hand side of the equation 5 is 0. So left hand side must be 0. Beta square minus alpha square is constant. So ultimately we can show that 0 to 1 x jn alpha x jn beta x is equal to 0. So we have already proved our question, that is 0 to 1 x jn alpha x jn beta x dx is equal to 0. This relation is known as the orthogonality relation of the Bessel's function. So I think you have understood that. For further understanding, I will refer to read the textbook of Das Verma Higher Engineering Mathematics, and thank you for listening the lecture.